Archimedes Principle and Upthrust is a new topic for physics this year, so I thought I'd make a video about the theory and do a few example calculations for you all. We start off by considering a volume of a fluid. The whole blue rectangle here is a volume of fluid, and within that we look at a control volume. So this fluid would be a liquid or a gas. For example, it might be water. It doesn't have to be water. This is my control volume here, which is enclosed by the dotted line there. Acting on this control volume of fluid, there is pressure from the surrounding fluid all the way around. Now that pressure is not uniform. The pressure increases with depth. So the pressure on the top is lower than the pressure on the bottom, and down the sides it's increasing. It increases according to the equation P is equal to density times G times H. It also has weight, so we can consider the weight acting through the centre of it if it's uniform density there. So we've got, and the other thing is this control volume is stationary. So that's what we've got, this control volume with pressure acting on it, and it has weight. We can see from looking at the pressure forces that the net pressure force, which I'm going to call F subscript P, must act vertically upwards. So if we look on the side, you can see that the net pressure force on this side is equal and opposite to the net pressure force on this side, because the pressure acting on it is identical. You can see from my illustration the arrows are identical and they're going in opposite directions. So the net pressure force on this side, which would be the mean pressure multiplied by the cross-section area, the surface area on this side, would be equal and opposite to the same on the other side. The net pressure force on the bottom is larger than the net pressure force on the top, which will give us a net pressure force for the whole thing acting vertically upwards. So there's Fp there. Fp must be equal and opposite to the weight in order for the block to be stationary, because there are no, the volume, so the control volume, for it to be stationary, because there are no other forces involved. There's just the net pressure force from the surrounding fluid and the weight of it. So Fp equals W, or Fp minus W equals 0. So it's balanced. So far, I've just been considering just a small volume of the fluid within the larger body of fluid. What would happen if I took an object that's not the same fluid, might be some solid object for example, that I put in this volume, and it has exactly the same volume, exactly the same shape? Well, in that case, the pressure force on that submerged object would be identical to the pressure force on the control volume. However, it has a different weight, because it's not that fluid, it's a different material, different substance. So the weight is not necessarily equal to the net pressure force, and in fact it's most likely not to be. They would need to have the same densities in order to have exactly the same weight. This net pressure force is what we call upthrust, so I'll call Fp, now I'll call it U, capital U. And the U is not balanced with W, so there is an apparent weight of the object. If let's say I put a steel block in water, then the density of steel is larger than the density of water, so the weight will be larger than the upthrust. That gives it an apparent weight in that fluid, so I put the steel block in some water with a Newton meter on it, and its weight will be less than if I measured it in air. Note that even when I'm measuring the weight of the steel block in air, there is actually an upthrust from the air that I'm measuring in. I'd need to measure it in a vacuum to measure the true weight. If you know the volume of the fluid that is displaced, then the mass of the fluid is the density of the fluid multiplied by the volume. That is assuming that it's uniform density. So therefore the upthrust, which is equal to the weight of the fluid, would be the density multiplied by the volume of the fluid that's displaced multiplied by G, because so mass times G gives me the weight, and I've just said the mass is density times volume. Good number to remember is the density of water, 1,000 kilograms per cubic metre. So that's useful to remember because you often do problems involving water. If we have an object that is floating on the surface of a fluid, so some of it is not submerged, then what do we have there? If it's floating and it's stationary, then it must be the case that the object's weight is equal to the upthrust, so the net force is 0. In this case, the volume of the fluid that is displaced is less than the volume of the object itself. And so for the object to be stationary, U equals W, that's the weight of the object, and the upthrust is equal to the weight of the fluid that's displaced. So what you need to know there is how much of the fluid was displaced. You could then work out the weight of that, that's equal to U, and you can generate your equations then, solve for the thing that you don't know. So those are some general principles for dealing with upthrust problems. Let's do an example calculation. For this, I have a steel block that's submerged in water. It has a volume of 500 centimetres cubed, so that volume of water is displaced. I need to calculate the apparent weight of the block when it is submerged. The density of steel is 7,850 kilograms per cubic metre. For this, I need to first convert the volume into SI units. So it's given in centimetres cubed. The prefix is 10 to the power of minus 2. So to convert this into cubic metres, which is the SI unit for volume, I'd need to do 500 times 10 to the power of minus 2 cubed, because it's a volume. So if it's a volume, you need to cube the prefix. That's the same thing as doing 500 divided by 100 cubed. That gives me 5 times 10 to the minus 4 cubic metres. Now the upthrust is equal to the weight of the fluid that is displaced. I've got the volume, I've just converted it to SI units. So the upthrust is the mass of the water, this is water I'm dealing with, multiplied by G, which is density multiplied by volume multiplied by G. Density of water, I've already said, is 1,000 kilograms per cubic metre, multiplied by the volume, multiplied by G, I get 4.91 newtons. So that's the upthrust. I haven't yet solved the problem. Now I need to work out the weight of the block. The weight of the block is the density of the steel multiplied by its volume multiplied by G. So putting in the values that I've been given in the question and this converted volume, I get 38.5 newtons. Again, still haven't solved the problem yet. So the weight minus the upthrust will give me the apparent weight whilst it's in the fluid, in the water. So W minus U gives me 38.5 minus 4.91, which equals 33.6 newtons. So that's the first calculation. Second calculation. Now I have a plastic cube which is floating on the surface of water. The length of the cube is 10 centimetres, floating water, it's stationary, calculate the volume of the block that is submerged in the water. The density of this plastic is 975 kilograms per cubic metre. So you could have a go at solving this problem now if you wanted to pause the video and have a go at solving it with that information, and I'll tell you the solution in a moment. Here's the solution to question 2. Firstly, the block is stationary, so the upthrust equals the object's weight, the plastic cube's weight. The mass of the block times g is equal to the weight of the block. So then I can say the density of the block multiply it by its volume multiplied by g is equal to the weight. I need to do another conversion and a calculation here. I gave the length of the block as 10 centimetres, so each of the dimensions of the block is 10 centimetres, so 10 centimetres cubed will give me the volume. However, I need to convert it into metres, so 0.1 cubed gives me the volume in cubic metres, so that's 0.0010 cubic metres. Now I can work out the weight. I've got the density here, density multiplied by the volume I just calculated multiplied by g gives me 9.56 newtons. I'm putting the dot dot there to say I haven't rounded this number. I'm going to use the raw number from the calculator in the next stage of the calculation. So I have the weight of the block. Next I need to calculate use the upthrust to do a calculation. The upthrust equals the weight, and the upthrust is equal to the mass of the water that is displaced multiplied by g, which equals the density of water multiplied by v multiplied by g. I've already given the density of water as 1,000 kilograms per cubic metre. So the volume of the water that is displaced is, if I rearrange this, upthrust divided by density multiplied by g. So I put my values in here that I've calculated. The upthrust is equal to the weight, this weight here, which is 9.56 dot dot, so that's where that value came from. There's density times g. So the volume of water that is displaced is 9.75 times 10 to the minus 4 cubic metres. The volume of the water displaced is the volume of the block that is submerged, so they're the same value. That's my answer. What this actually means, though, is that most of the block is submerged. You can appreciate that that is pretty much equal to that volume. It's just a little bit short of that volume. So a more accurate diagram would be this. Most of the block is submerged. Those are some calculations. Hopefully that will help you get your head around the theory. Let's look at some different scenarios that you may encounter with upthrust. Here's a plastic block which is submerged fully under a fluid, and well, this is plastic in water, so it's submerged in water, and if you release a plastic block under water it will float upwards. So first scenario is something floating upwards, such as a plastic block submerged in water which you then release. Here the upthrust is greater than the object's weight, giving us a net force that is upwards, so you get this upwards acceleration. In this case, the weight of the displaced water is greater than the weight of the block, meaning that the upthrust would be bigger. And that would give us, if we were to measure the apparent weight, it would give us a negative apparent weight, which means that the apparent weight is upwards. If you do W minus U, you get a negative value. So it means that the net force is upwards, basically. Another scenario, here you have an object that is sinking, so you've got a steel block in water and you release that, it will sink. So here the weight of the object is greater than the upthrust, giving us a net force that is downwards. So here the weight of the displaced water is less than the weight of the block. This is displacing water equal to its volume, and the weight of that water is less than the weight of the block itself, giving us a smaller upthrust than the object's weight. So the apparent weight was positive there, it's downwards. Another scenario where we have something that is floating at neutral buoyancy, we would call this. And I've got a polystyrene block here which is floating on the surface of water. Another example of this would be an airship that is stationary at constant altitude. And submarines. Submarines can alter their neutral buoyancy, and that would mean, right, did I say that right? Submarines can alter their buoyancy by pumping water into or out of ballast tanks So the submarine can dive and then it can adjust its buoyancy overall so that it has neutral buoyancy, and then it would be stationary at a constant depth. In these cases, the weight is equal to the upthrust, giving you net force equal to 0. The weight of the displaced water is equal to that of the block. In this case, you can see that the displaced volume is not equal to the total volume of the block. So the weight of this volume of water is equal to the weight of the block in this case. Slight variation on that. If I switch my polystyrene block for a polythene block, slightly heavier, then I can have neutral buoyancy again. So this object has got the same volume, but it has greater density, and it's in the same fluid. Okay, so the fact it's in the same fluid is important here. My polythene block floating in water. The weight of the block is still equal to the upthrust, giving me a net force of 0. So the explanation of this is that an object with larger weight needs to displace more water in order to have a larger upthrust, giving it 0 resultant force. So in order to do that, it needs to sink further into the water. So that's what I showed when I replaced the block with polythene. It sank further in, displaced more water, larger upthrust. I'm going to keep my polythene block this time, but now I'm going to replace the water with salt water. So it's still neutral buoyancy. This is the same object, but in fluid of larger density. Polythene block floating on salt water. Salt water has a slightly higher density than non-salt water, fresh water. The forces still W equals U. The net force is still 0. An object with the same weight needs to displace less of the more dense fluid to achieve neutral buoyancy here, so it will float higher above the surface. So I'll say that again. The object has got the same weight, but the density of the surrounding fluid is now larger. So if you displace the same volume of it, the weight of the displaced fluid would be larger. So it doesn't need that much upthrust. It doesn't need a larger upthrust, it needs the same upthrust, so it displaces less volume of the fluid by floating higher above the surface. I hope that made sense. That was not a very good explanation. If you've got any questions about that, then do put it in the comments. Lastly, I'll finish up with a proof that the upthrust is indeed equal to the weight of the fluid that's displaced. I have a cube that is submerged. This is the cube of the same fluid. Well, I'm assuming it has uniform density, and the sides are all length L. I've shown the pressure forces acting on it. As I noted before, the main point is that the pressure on the top surface is less than the pressure on the bottom surface. So I've labelled the pressure on the top surface as P1, the pressure on the bottom surface as P2. The net pressure force due to P1 on the top surface is F1. The net pressure force due to P2 on the bottom surface is F2. The top surface is at a depth of H1 from the surface of my fluid, and the bottom surface is at depth H2. So that's my cube. The horizontal pressure forces on the side cancel out. We've already mentioned that because the pressure is symmetrical, so the net pressure force will be equal and opposite on those two sides. The pressure forces on the top and bottom are unequal, so that's where we get a net force. There's a net force in the vertical direction, and we already can appreciate that this force is larger than this force, so we know it's going to be upwards. If we look at the top surface then, pressure 1, using the pressure equation rho GH, so pressure at a certain depth in a uniform fluid, P1 is equal to the density of the fluid multiplied by G multiplied by the depth, which is H1. So the force due to that pressure is pressure times the area, because pressure is force over area. So now I can say substitute for pressure into P1 here, and I get F1 equals rho GH1 times A. A is the area of one side, which would be L times L, though we don't need to break that down. On the bottom surface, P2, do exactly the same procedure as rho GH2, so F2 is rho GH2 times A. The resultant force is the upthrust, so U is F2 minus F1. I've taken upwards as positive because I know that F2 is larger than F1 and U will act upwards, so I've taken that direction as positive. If I take this away from this, so it's rho GH2A minus rho GH1A, then I get this, rho GA multiplied by H2 minus H1. H2 minus H1. That length minus that length just leaves me with this, which is equal to L. So U then is equal to rho GA times L. A times L is the volume. That's that area multiplied by that length. Rho V is the mass of this cube here, which we'll call M. So U is equal to mg if I substitute for rho V in that equation there. So I get mg. The upthrust on that cube is equal to the mass of the fluid multiplied by g, so the weight of the fluid. And there you go, you have the proof that the upthrust is equal to the weight of the fluid that is displaced. Hope that was helpful, and if you have any questions, put them in the comments down below.